Have you ever dreamed of stepping into a machine and reappearing instantly on the other side of the world? It sounds like pure science fiction, a staple of shows like Star Trek. But what if I told you that the seeds of this technology are not only real but are being explored in labs right now? The secret lies in the weird and wonderful world of quantum mechanics. So, grab your thinking caps, because today we're diving deep into the question, what if quantum particles held the key to teleportation? First, let's clear up a common misconception. When we talk about quantum teleportation, we're not talking about physically sending a person or an object from one place to another. We're not deconstructing atoms and reassembling them elsewhere. Instead, we're talking about transferring information, the exact state of a particle, from one location to another, without that information physically traveling through the space in between. It's less like a teleporter and more like a cosmic fax machine, but infinitely more complex and fascinating. To understand this, we need to meet the star of our show, the qubit or quantum bit. In classical computing, a bit can be either a 0 or a 1. It's a simple binary choice. A qubit, however, is a game changer. Thanks to a principle called superposition, a qubit can be a 0, a 1, or both at the same time.
Think of it like a spinning coin. While it's spinning, it's neither heads nor tails. It's in a state of both possibilities. Only when it lands, or when we measure it, does it settle into one definite state. This ability to exist in multiple states at once is what gives quantum particles their immense informational capacity. Now let's introduce the second mind-bending concept, quantum entanglement. This is what Albert Einstein famously called spooky action at a distance.
When two particles become entangled, their fates are linked, no matter how far apart they are. If you measure one particle and find it has a specific property, you instantly know the corresponding property of its entangled twin, whether it's across the lab or across the galaxy. Imagine you have two of those spinning coins, but they're entangled. The moment one lands on heads, you know without a doubt, the other has landed on tails. There's no signal sent between them. Their connection is instantaneous and fundamental to their nature. So how do superposition and entanglement come together to make teleportation possible? Here's a simplified breakdown. Let's say we have three particles. Particle A, which is the original particle we want to teleport the state of. Particle B, which is here with A. And particle C, which is far away at the destination. Particles B and C are an entangled pair. First, we interact particle A with particle B. This interaction causes a joint measurement that entangles them. Because B was already entangled with C, this new measurement effectively transfers the original quantum state of A onto C. It's like a chain reaction of information. The weird part is, in the process of this measurement, the original state of particle A is destroyed. You can't just copy quantum information. The no-cloning theorem forbids it. You can only move it. So, we perform our measurement on A and B. The result is just a couple of classical bits of information. Simple zeros and ones. We then send this classical information to the person holding particle C. This information can be sent via any normal method, like an email or a radio signal. This part is not instantaneous. It's limited by the speed of light. When the person at the destination receives our classical information, they use it as a key. It tells them exactly what kind of final adjustment to make to particle C. Once they perform that simple operation, boom, particle C is now in the exact, identical quantum state that particle A was in at the beginning. We haven't moved the particle itself, but we've successfully teleported its complete identity, its soul, if you will, from one place to another. Scientists have already achieved this on a small scale. They've teleported the quantum states of photons, atoms, and even more complex systems over dozens of kilometers through fiber optic cables and even to a satellite in orbit. This is a monumental achievement, proving that the theory works in practice. So the big question remains, can we scale this up to teleport a person? This is where we leap from reality into the realm of profound speculation. A human body contains an astronomical number of particles. We're talking about something like 10 to the power of 28 atoms. To teleport a person, we would need to scan, entangle, and transfer the exact quantum state of every single one of those particles simultaneously. The amount of data required would be staggering, beyond anything we can currently comprehend. We're not just talking about the position of each atom, but its energy level, its spin, its momentum, its entire quantum identity. Storing and transmitting this data would require a computer with more memory than all the computers on Earth combined, by many orders of magnitude. The energy needed to perform the scan and measurement would be immense. Furthermore, there are philosophical questions. If you teleport, is the you at the destination truly you? Or is it a perfect copy, while the original you was destroyed in the scanning process? Does your consciousness, your memories, your very sense of self transfer along with the quantum information? These are questions that venture into the territory of metaphysics, far beyond the scope of current physics. But let's not get discouraged. While teleporting humans remains a distant, perhaps impossible dream, the implications of this technology for other fields are revolutionary. The most immediate impact is on quantum computing and the quantum internet. Imagine a global network where information is perfectly secure. Because measuring a quantum state disturbs it, any attempt to intercept a quantum communication would be instantly detected. Quantum teleportation would be the backbone of this unhackable internet, allowing us to transmit quantum data between quantum computers located anywhere on the globe. This would unlock unprecedented power for scientific research, drug discovery, financial modeling, and artificial intelligence. It could also revolutionize sensing and measurement. By teleporting the states of sensitive quantum probes, we could create incredibly precise sensors for everything from detecting gravitational waves to performing medical diagnostics at the cellular level. The journey from teleporting a single photon to building a quantum internet is long and challenging, but it's a journey we've already begun. Each successful experiment, each new breakthrough, brings us one step closer to harnessing the universe's most fundamental rules. What started as a spooky curiosity is now a cornerstone of next-generation technology. So, while you might not be beaming up to the Starship Enterprise anytime soon, the quantum world is promising a future that is, in its own way, just as exciting. A future of unbreakable security, unimaginable computing power, and a deeper understanding of reality itself. The key, it turns out, was hidden in the strange, beautiful dance of quantum particles all along. Thank you so much for joining me on this journey through the quantum realm. If you enjoyed this exploration of the future, don't forget to like this video, subscribe to the channel, and hit that notification bell so you won't miss our next deep dive. What other futuristic technologies do you want to learn about? Let me know in the comments below. Until next time, stay curious.